I'm happy to introduce my colleague and friend, Yasir Khan, Dr. Khan. Um, Yasser is now a postdoctoral scholar at Stanford. He's advised by Professor Zenon Bao in chemical engineering and Professor Boris Merman in electrical engineering at Stanford. He completed his PhD in electrical engineering and computer science at UC Berkeley under Professor Ana Claudia Arias, and he received his BS and his MS in electrical engineering from the University of Texas, Dallas, and King Abdullah University of Science and Technology, respectively. Yasser's research focuses on additive manufacturing and hardware AI to produce skin-like wearables and implantable devices. And these medical devices are being used for precision health and psychiatry. So really interesting variety of diverse applications. Yasser is the recipient of multiple awards. He received the EECS Departmental Fellowship at UC Berkeley, the Discovery Scholarship and Graduate Fellowship at KAUST, as well as an Academic Excellence Scholarship at UT Dallas. Yasser's authored over 40 research publications and has presented at a number of conferences. Some of his work has been highlighted by BBC News, the Wall Street Journal, NSF News, and a variety of other sources. So I'm very pleased to introduce Yasser and looking forward to the talk he'll give today on oximetry and ventilators and some, I think, highly topical and relevant medical devices and some interesting technology behind it all. So thank you, Yasser, and we look forward to your presentation.
Thank you for the kind introduction, also invitation to present in this interdisciplinary platform. I like these kind of presentations because it generates so much discussion and new ideas. I'll share my screen. Okay, hello everyone. Today I'll be talking about two really important medical devices now, oximeters and ventilators for battling COVID-19. Just a brief background on me. I got my bachelor's from UT Dallas in electrical engineering in 2010, where I worked on mostly electrical engineering, material science, and photonics. And I worked on making extremely sharp tips for scanning and tunneling microscopy. And then I moved to KAUST in Saudi Arabia, where I studied photonics, where we studied the light capturing capability in chaotic microstructures. Then I started my PhD at Berkeley. This work I'll be talking about today on bioelectronics and biophotonics. And also I worked on flexible hybrid electronics. These are where you essentially merge in two types of electronics, soft electronics and conventional silicon electronics. And finally, at Stanford, I'm basically translating what I did at my PhD and also expanding to precision health and precision psychiatry. We are using a similar soft materials. And at the beginning of COVID-19, I also started working on ventilators that I'll be sharing today. So during my PhD and postdoc, the vision I had is essentially how can we go away from a photo like this? So if you walk into the hospital, you'll see these big machines with all these wired sensors connected to the patient. And these are not that comfortable. So our vision was to create something soft and which is conformable that's creates a good interface with the skin. So a device similar to the skin and that can sense most of the vital signs. And we worked on ECG, oxygen saturation, temperature. So a lot of biosignals you can actually extract from these skin-like electronics. And the benefits of flexible and stretchable sensors, we saw in one of these projects where we were trying to read the impedance of the skin. And at the beginning of the project, we were using rigid PCBs. And here you can see, if you use a rigid PCB, these are not soft and not flexible. And they are bulky, they are not comfortable to wear. And most importantly, you don't get a good skin interface. And then we started looking into how can we make soft and flexible sensors. So here we have a bandage-like sensor that does the exact same thing as the rigid one, but here we saw an improvement in signal to noise ratio. And this is the bioelectronic aspect. We saw the same effect in biophotonics. So here you can see we are using a light source and a light detector to look at oxygenation. I'll talk about that later in the talk. And when you have a sensor that wraps around the finger, that gives you a better signal because it cuts out all the ambient light. And it's not just wearables. We can see a similar benefit in even implantables. So here is one example where you have an artery and then there is a sensor that wraps around this artery. So with rigid electronics, we cannot do that. We need soft electronics to do a sensing like this. So with all these benefits, we can create new types of medical devices, and they are opening up new applications. I'll talk briefly about the fabrication aspect of this kind of new flexible electronics. So right now, photolithography, where you basically deposit a blanket layer of material and then selectively remove those are used for making flexible and stretchable electronics. And those are called photolithography. It's standard in silicon manufacturing. What we try to do is we try to go to an additive manufacturing way where we are essentially printing the functional material. So one example is we can print gold nanoparticle ink, and that will give us these fine electrodes. And then there's another modality of printing. It's called blade coating. So here you will have a blade that goes on top of a substrate and spreads the material. So these are large area processes. So you can process a huge substrate with printing. And also another approach is screen printing. Here you can see we will have a screen, and then the pattern is within this mesh, and it gets transferred when you have a squeegee that goes over the design. So with this, we can create bioelectronic and biophotonic devices. And we were able to use these devices in many parts of the body. So we saw that you can essentially put it on the wrist, on the chest, and also leg. So a variety of biosignals you can collect with all these flexible and stretchable sensors. And I like to classify these different type of sensing into three main categories: bioelectronic, biochemical, and biophotonic. Bioelectronic is, let's say you're dealing with a voltage or a current signal. Biochemical is mostly used for sweat sensing or in saliva. It's done in bodily fluids. And biophotonic is the one I'll be talking about today. That's for using light, and with light we can detect vital signs. So to give an overview of my research, I essentially use large area additive manufacturing to create multimodal sensors, circuits, and with those we can enable new applications. And since we are generating a lot of data, we can now look into hardware and software AI, and also merge with conventional silicon-based electronics. So here we are taking engineering concepts from materials manufacturing, design, devices and circuits, and we are enabling new applications by making implantables, wearables, ingestibles. And these are allowing us to do precision psychiatry, precision health. I'll talk about this in a later talk. Today I'll be talking about the Oximeter project. So the Oximeter is now super relevant because, COVID-19 is a respiratory illness. Essentially, your respiratory system gets attacked. And over time, the gas exchanging capability of lungs reduces. So that reduces your blood oxygenation. And one big problem of hypoxia in COVID-19 is the patients don't actually feel it. So there are reports saying that one example is in a Scandinavian country, there was a person, he didn't feel anything, but his lips were turning blue. And when he measured oxygenation, it was close to 70. So typically you need oxygenation over 95. So this is a huge problem. So that's why we are now focusing in oximeters, and oximeters are now becoming the new thermometers. So what is pulse oximetry? It's a really standard method of measuring blood oxygen saturation. So if you see these monitors in hospitals, they usually have a pulse ox information. And the way the measurement works, it's an optical measurement where you have two different lights. They shine through the finger. And then with the sensor, you detect the changes in light. When the heart pumps blood and then retracts blood, it creates this pulsatile waveform. And if we use two different colors, then we can create a ratiometric measurement. So blood oxygen absorption in the different ranges of color, let's say red and near infrared, it's quite different. So we can use these two different colors to get a ratiometric measurement of blood oxygenation. So typically you will see this kind of finger clip sensor to measure oxygenation. And on one side you have the LEDs and the other side the photodiode. What we try to do is we try to create a flexible band-aid light form factor for this kind of device. So you can essentially wrap it around the finger and it's much more comfortable. And we started looking into how can we make a flexible oximeter. So the problem here, we are dealing with optoelectronics. Those are inherently rigid if you use conventional electronics. But if you go into organic electronics, you can make devices, those are thin, flexible. And we are using OLEDs, organic light emitting diodes, and also organic photodiodes. So with these, you can make devices, those are thin and flexible. And we started looking into what are the fundamentals of measuring oxygenation. So the way I said, like oxygenated and deoxygenated blood, they have different absorption in the spectra, light spectra. So here I'm plotting the ratio of the absorption. And here you can see in red and near infrared, you have a big contrast. So typically standard oximeters, they exploit this property where they use red and near infrared light. But in making a highly efficient near infrared OLED is difficult. So that's why we used red and green light. And we were able to show that with organic optoelectronics, we can actually measure the exact same signal you can measure with commercially available oximeters. So here, there are two different panels. These are the photoplethysmogram signal, PPG signals from near infrared and red. And this is from the red and green, the device we created. So this was the first demonstration that we can actually use organic optoelectronics to measure oxygenation. And we were able to measure pulse rate and oxygenation with errors of 1 to 2%, so which are really low. Essentially validating the idea that we can use this kind of novel optoelectronics to measure oxygenation. And then the idea was we are making a band-aid. So with this type of measurement where you have the light on one side and the detector on the other side, you are limited to several parts of the body. So the fingertips, the toes, and earlobes, here you can do the transmission mode measurement because these are thin layers of tissue light can penetrate. But if you go into the reflection mode, you actually can put it in different parts of the body. So that's why we started looking into reflection mode oximetry. And the first thing we did is we looked into like where in the body we have a good PPG signal. And it seems the forehead is actually the best place to measure reflection mode oximetry, but we saw signal around the body. You can actually measure reflection mode signal in various parts of the body. And then another good part with printing is we can design sensors. Those are not constrained to the conventional square form factor. So here you will see in a conventional geometry, you will have the sensor in the middle and the light emitters on both sides. But with printing, we can actually make devices that wraps around the sensor. So that increases the signal to noise ratio. So here I'm showing a study where we compared the standard geometry to the new geometries, the bracket and circular designs we were able to print. And these essentially increase the signal by twice. So with this kind of printing, we were able to get a better signal. And now I'll just briefly show the math and the analytical model that goes behind making a reflection mode oximeter. Essentially, you will have a incident light, and then that goes through exponential decay based on skin, tissue, and bones, and oxy and deoxyhemoglobin. And from here, you can analytically calculate what's the oxygen saturation if you're using two different colors of light. And we showed that the same principle that is standard for transmission mode oximetry applies to reflection mode pulse oximetry also. And once we validated the device and also the model, we went to a reflection mode measurement. Here, it's on the wrist. We are basically doing the same measurement with red and green light. And we were able to produce same PPG signal and oxygenation. So at that point of the project, we got a bit stuck because we were taking measurement from healthy patients. So when I say healthy, mostly your oxygen saturation will be over 95. And but to validate our setup, we wanted to go below 95. So we looked around what can be done to do a measurement where we can actually reduce the oxygenation. And one of my friends, he's a cyclist and he does high altitude biking. And he mentioned that he uses this altitude generator. So this essentially changes the amount of oxygen you breathe in, and that changes your oxygen saturation. And then I said, okay, let's give it a try. It was hard to get an IRB, but we tried that. And so this is the result, where here you can see the first panel. So normally we breathe 21% of oxygen. And then we can, with this machine, we can reduce it down to 17.5 and then 15 and see what's the response in SpO2. And we put one commercial probe on the finger and one reflection mode probe on the forehead. And here you can see the SpO2 level tracks really well for both the devices, even if you change the oxygenation. So that was really good. It's essentially validated that with lower oxygenation, we can use our device. And then we started looking into how can we actually have multiple pixels, because now our single pixel measurement is validated. And then we created one wristband where we have multiple pixels. And here you can see the signal on the wrist and the radial and ulnar artery, they're quite different. The highest signal is coming from the radial artery. And most smart watches, they actually measure from the wrist. So if you put a sensor that goes on the radial artery, that increases your signal quality. And with the multi-pixel setup, you can essentially do statistical models to find out what is the best pixel and then weight that pixel. And even if one pixel is a bit noisy, you can rely on the other pixel strength. So that's how we showed that with multiple pixels, we can measure oxygenation here. And so this project has been running for over throughout my PhD. And then we were in touch with doctors at UCSF where they saw the results we have from the single pixels. And then they suggested, why not make an array of devices? And with those, you can actually map an area of tissue. And this will be really useful to, let's say, looking at skin grafts. And this one was quite difficult because here we're dealing with multiple pixels and how to process the data, collect the data, and clean out the data. But we actually give a good amount of effort, and we were able to create this oximeter array. So here you can see multiple layers of optoelectronics. They are designed in a checkerboard fashion. So you can do one pixel measurement and then move to the next. And that allowed us to create a oxygenation map. And we basically used printing techniques to create these optoelectronics. So here I'm showing the flow for making the light emitters, and this is for the light detector. And once we made these devices, so this is the OPD array. So these are the sensor, and this is the light emitter. So you can see eight pixels here. They have different emissions. One is in the red and another is in the near infrared. With this device, we can actually create a map. So here we can see we light up one pixel, move to the next one, and then essentially create a raster scan of the surface. And that raster scan gives you a map of oxygenation. And then we also validated that what happens if you don't have a PPG signal. So when you are measuring oxygenation, there are two different methods. One is when you have the pulsatile signal with the PPG. And when you, let's say, cut off the blood supply with a pressure cuff, the PPG signal goes away. So then it becomes quite tricky to get the signal. So we actually created another model to get oxygenation when you don't have a pulsatile signal. So with all this, we were able to show oxygenation measurement in 2D in a patient where we change the oxygenation of the arm, and then we can essentially create this nice 2D plots of oxygenation. So this is super cool, and it essentially validated our approach of 2D oxygenation monitoring. And hopefully, so right now we are actually actively pursuing other clinical direction where we will put this on tissue and skin graft. And then also another extension of this project was, can you measure oxygenation with ambient light? So this was a thought experiment we had, and here in the previous one, we had controlled light sources, LEDs, but in this one, we don't have a light source. We are relying on ambient light, and we are using filters. So these filters gives us selectivity to select the red, near infrared, different bands of light. And with those, we can actually measure oxygenation. So here I'm showing four different lights: sunlight, fluorescent light, LED, and incandescent light. And you can see PPG signal for most of them. And for LED, I believe it didn't have the near infrared contribution. So that's why we don't have a PPG signal in the NIR for LEDs. But so this is something it's worth exploring because PPG is essentially self-calibrating, and we can try using ambient light to measure oxygenation. So I started the flexible oximeter project at the beginning of my PhD, and it's great to see the continuation of the project because like the whole research community, they contributed, and we can see the evolution of flexible oximeters. So in 2014, we showed that organic oximeters can be used. And then in 2016, Takao Somiya's group showed that it's possible to make really thin sensors. So they were showed that it can be done with a 2 micron thick sensor. And then Professor Rogers' group also showed that with conventional electronics, you can do oximetry. And then we showed that it's possible to use a red and green light to do reflection mode, and then finally the array. So overall, we saw a great improvement in the last 5-6 years in flexible oximeters. The reason I mentioned this is because like after we published the paper in 2018, I got this email from a mother of a 5-year-old who suffers from epilepsy and autism. She was saying that her son, he doesn't want to keep any watch or the existing wearables. And it's really important that the community comes up with a soft, wearable, and comfortable device where we can actually measure oxygenation. And this is actually will change lives for many people. So still the overall research community is contributing, but I think we need further commercialization of this kind of soft electronics to make it happen. All right, so I'll move into the second part of the talk where I talk about the other important medical device, that is the ventilator. So I believe everyone heard about ventilators by now. This is one of the main medical devices that provides respiratory support to COVID-19 patients. But in this case, I'll focus in a different view. I'm gonna show how COVID-19 is affecting other countries other than the developed countries. So I am from Bangladesh, and we have roughly 160 million people. The land area is roughly same as Illinois, and we have almost half as US population. So that makes social distancing and and also the lockdowns really challenging because we have other socioeconomic challenges to address. And also we don't have enough resources medically to treat a huge amount of COVID-19 patients. So that's why I essentially, like at the beginning of the pandemic, we started looking into how can we contribute and how can we create a ventilation solution that is easily deployable to countries like Bangladesh. And right now, if you look at the initial stage of COVID-19 treatment, so as I mentioned, if your oxygenation goes down below 93, 92, it's risky. And if it goes much below than 80 or 70, then you need intubation with mechanical ventilation. So that was the norm at the beginning. And what people saw is with intubation, the mortality rate is really high because here you're essentially putting an endotracheal tube inside the patient, and those patients didn't respond. And a few studies from Italy at the beginning reported roughly a 60% of mortality rate for intubated patients. And the reason I'm bringing this up because let's say we have different type of ventilation solution. One is invasive ventilation where you put the tube inside, and then the other ventilation is done with face mask. So these are called non-invasive, and the invasive where you will have a tube inside. And what we saw from earlier reports with intubated patients, there are other complications that normal hospitals without ICU support cannot handle. And for those hospitals, it's good to go with a non-invasive solution. So I'll give you just a perspective in Bangladesh. So here I'm showing in one of the COVID dedicated hospital in Bangladesh. And this is a reporter. She's gonna walk through and show what's the available resources in Bangladesh. And so and on May 24th in my city, I'm from Chittagong in Bangladesh, we have a population roughly 16 million. And at that time we had only 10 dedicated ICU beds. So when we talk about invasive ventilation, we need the ICU support. And here she's showing the rows of beds, and these only have a oxygen cylinder, and this cylinder can give you 15 liters per minute. We don't have the ICU capacity to facilitated invasive ventilation. So that's why we started thinking about like how can we make ventilation easier. So let's walk through what is the normal protocol for treating COVID-19 patient. So let's say someone comes in the hospital and his or her oxygen saturation is below 92. People usually start with a nasal cannula here, and they are given 1 to 6 liters per minute oxygen. And if you still don't get a oxygenation over 95, then you go to a face mask where you give 5 to 10 liters of oxygen. Still you don't get a response, then you go to the next level. This is a non-rebreather mask where you give roughly 15 liters per minute oxygen. And very severe patients, they don't respond to this kind of um, respiratory support. So they will need high flow nasal cannula or CPAP. CPAP is continuous positive airway pressure. So this essentially forces the air with pressure, and that increases your oxygenation. So we thought that these two non-invasive solutions are suitable for even in these countries. Actually, people are now preferring non-invasive solutions. But the problem is when we talk about a high pressure machine and we have a virus, there is a possibility of aerosolization. So here we are showing a CPAP. It's you can see, like when you turn on the machine, it's roughly gives a high pressure close to 10 to 15 centimeter of water. And with that, you actually generate a lot of aerosols. So this aerosolization is actually a big problem. And the way we thought about it is how can we address this? And one solution is to use a helmet. So we use the same machine that gives you a high pressure, but we contain the spread of the virus using a helmet. So this way, we are providing the necessary respiratory support, but the patient is breathing within the helmet, and that's restricting the spread of the virus. Right now, like you will see a lot of makeshift ventilators using these bag squeezer designs. The problem with these is these are mostly designed for the invasive ventilation. And when you go to invasive ventilation, it's essential to make sure that it works properly. And these systems are error prone because here, this is a mechanical system with a lot of parts, and many things can go wrong. And in India, they actually deployed thousands of these units, and these were not performing as with all this in keeping all these design constraints in mind. We decided to go with a non-invasive ventilator that is easy to use. And also we designed a patient interface with the helmet. So here you will take, excuse me, is my connection unstable?
Sometimes when you speak, it's gone in and out, but you're clear now.
Okay. I'm sorry about that. Yeah. All right. So here you can see we have the air supply. You can use room air and also oxygen. And these two air source will come to the ventilator. And then this can actually provide airflow of 6 to 160 liters per minute and air pressure of 0 to 20 centimeter of water. We basically designed this in 6 weeks. We brought in people, mostly Bangladeshis in Berkeley and Stanford. We made a team and we created this design, which is easy to use and low cost. That's really important because we want to make this in bulk. The way the system works is we have a blower. So this DC blower, it compresses air, And we have a motor controller that controls the blower. And then to control the unit, we have a microcontroller and also a touchscreen display. And we have a way to log the data in a SD card. We also have a real-time clock, and it has a bunch of sensors for pressure, flow, and also we have a oximeter connection. And on the patient side, we have this helmet. And here you see in the inlet side, we have a viral filter. And also on the other side, we have a viral filter and the PEEP valve. The purpose of the viral filters is to restrict the spread of the virus. And the PEEP valve essentially contains the pressure. So you can change the pressure from the ventilator and also from the PEEP valve. And we wanted to make the UI really easy to use. Basically, you change the setting here and press start, as simple as that. And with that, we can actually provide the respiratory support. So here I'm showing the NIV system. It's quite small. It fits in a 8-inch by 8-inch by 4-inch box. And we have minimal setup to hook this up with a patient. And we can do CPAP. CPAP is when you have a fixed pressure. BiPAP is when you inhale and exhale. During the exhalation, it reduces the pressure. So it's a bilevel pressure mode. We can do 60 to 160 liters per minute, and also the pressure can be set. I ratio, that's inspiratory to expiratory ratio. Here you also have a control. And also you can change the breaths per minute. We also put in alarms for leak and disconnects. We made 5 units for the first batch. 4 of them are in Bangladesh. 1 is in Bolivia. They are now going in a clinical trial. I'll show the results. And we also checked the pressure and flow reproducibility. So here I'm showing the 5 devices, basically what, this is the pressure you set, 5 centimeter of water pressure, 10 and 15. We essentially get a really good reproducibility, batch to batch reproducibility. And also we can get a good flow. The flow is important because in an enclosed setup where you're wearing the helmet, if you are not maintaining a good flow, there will be CO2 rebreathing. Essentially, when you breathe out CO2, that gets trapped within the helmet, and that's detrimental. Also, we did flow reproducibility testing where we checked for 60, 100, and 140 liter, ran the devices for a long time. For here, we're showing data for 4 hours, but it can actually go for days. And as I mentioned, it has 2 different modes. One is CPAP, another is the BiPAP. In the BiPAP mode, here you can change the levels. And during the expiratory phase, here you can actually see a reduction of pressure. And we checked this that works with most of the standard setting people use in a BiPAP. And as I mentioned, the flow is really important because if you don't have enough flow, your CO2 will be trapped and you will start rebreathing the CO2. And what we saw, if we maintain an adequate flow over 60 liters per minute, it's much more comfortable wearing the helmet. Here I'm showing the unit in action. So here, basically, you can see the helmet. It's easy to wear. And on the inlet side, you have the viral filter and connection from the NIV. The outlet side, you have the viral filter and the P valve. And this is controlled, set the unit up, and then start running. And now I'm just showing that I can measure oxygenation. So we did the initial study, and we then started looking into what are the different oxygen delivery interfaces. So here we have an oral nasal mask total face mask, snorkel mask, and helmet. And we also explored like how the NIV system responds to all these oxygen delivery interfaces. And what we saw is we were basically trying to figure out what's the best setting to run the tool. And with 15 centimeter water pressure and 15 liter per minute oxygen flow, we were able to generate a good PEEP. Okay, so this is the helmet with 15 centimeter CPAP pressure, room air, and now we are mixing that with a 15 liter per minute oxygen flow. So it essentially the same. So we don't see much variation from a commercial NIV. Our device works almost similar. And we also did a pressure comparison here. PEEP means peak inspiratory pressure, and PEEP is peak and expiratory pressure. When the doctors deal with NIV systems, they mostly deal with PEEP, and a higher PEEP essentially keeps your alveoli open, and that recruits more alveoli. That's good for the COVID-19 patients. And one interesting thing to point out is, let's say you set a 12 centimeter water pressure, and typically for a normal system, you'll get the same PEEP. But since you have a large volume here for the helmet or the snorkel mask, your PEEP goes down. So that's why we wanted to show this data. And like a lot of people from around the world reached out to us asking for what setting we are running this device, because this is a key finding that allows us to use the helmet with the NIV, where you need a higher initial setting to get a higher PEEP. And with this setup, you can actually start treating patients with severe respiratory infections. Also, we did flow FiO2 and inspiratory CO2. As I mentioned, CO2 is a big concern. You have to make sure that your inspiratory CO2 is low, and FiO2 is how much oxygen is in the air. So here also, we showed that this actually performs within the standard model. And we do have a inspiratory CO2. And finally, one thing to point out, a big discomfort. Using the oral nasal mask, you get air pushed directly on your face, and that's really uncomfortable. And it's evident from the data here. So here you can see the pressure builds up, and then it goes down when you inhale. But with the helmet, you don't see that. With helmet, we get a reliable, repetitive signal. So this is much more comfortable compared to the standard oral nasal mask. And we are using a guideline recommended by NHS UK, where I'm not going to go into the details. Essentially, here we follow what setting to use based on standard CPAP. And these are the clinical trial results from Bangladesh, as I mentioned. So these are now used on patients in Bangladesh. So here I'm giving one example. At the beginning of the ventilation, this patient, when I say SO2, so this is the arterial oxygenation. It was roughly 87%. After 20 minutes of helmet ventilation, it went up to close to 96. So this actually validates that this setup with the helmet and the NIV works, and it works really well. And the doctors are quite impressed with the results. And we are continuing the testing right now in Bangladesh. And here I'm showing results from 5 different subjects. This is male 67, female 70, and then male 50, male 65, female 46 years. And for all of them, the plot essentially shows the change in oxygenation. Over 95, it's good. If it's below 92 or 93, that's not good. We try to recruit patients who have oxygenation below this red line. And what we saw with 30 minutes of ventilation, roughly on average, we see close to 8% change in SpO2 for the patients. So this is really encouraging, and we are continuing this trial. And hopefully, once we publish this, other countries can actually getting requests from all over the world, Kenya, then Colombia, many countries, doctors from many countries, they are reaching out to us to ask how can they use NIV with the helmet. And I think this is one of the way we can implement this setup in a large quantity, and this is scalable. And I want to also mention this. This is a open source full-featured ventilator initiative from Stanford. You can check this out. All the designs are available. The previous one I talked about, that's for non-invasive. This one is has also invasive. So this is roughly there are over 10 companies and institutions collaborating on this project, hundreds of engineers working around the clock to make this happen. And we are at a point that we can also start a clinical trial of this machine. All right, so finally, I would like to acknowledge the two amazing groups I have been part of during my postdoc and PhD. Professor Zenon Bao at Stanford and Professor Ana Claudia Arias at Berkeley. I've been really lucky to be able to collaborate with many, many people. And I also have to acknowledge all the funding agencies that helped my research. And finally, I would like to dedicate the ventilator work to my mom in June. And it was questions, I can take those.